Hey, great to see you again. Mr. Smith here. In today's slide deck, we're going to be very focused. What I want you to do is to pause the deck often and make sure that you get good quality notes out of it. I'm going to give you all the basic concepts that you're going to need to understand the topic of mechanical waves. So first thing, what's a mechanical wave? Well, a wave is a way of sending energy from one place to another, and a mechanical wave is a certain category of that. So if I have a slinky and I wave the slinky carries the wave energy. If I have water and I drop a rock in it, the water carries the wave energy. And you're going to see a theme here. If I have sound energy is carried by air. If I have a garden hose, I can whip that garden hose to one side and send energy from one place to another place. So what's a mechanical wave? It's a way of carrying energy that requires a medium. So a medium is the thing that does the waving, and that's what makes it mechanical. Okay? So the second big thing you want to understand about mechanical waves is that the medium is the thing that does the waving, and that's the thing that determines the speed of the waves. So very different from a thing like a baseball, where if you throw it faster, it carries more energy. Waves don't work that way. The medium, the thing that's doing the waving, determines the speed. So there's a couple different kinds of waves. Let's first of all look at one called a transverse wave. So in transverse waves, you're going to see a pulse and a slinky go from right to left across your screen. And what you want to look for is the fact that the little tape piece in the middle just bobs up and down. That's transverse. Transverse is another word for perpendicular. The medium moves up and down, but the wave energy goes side to side. So transverse, wave type number one. So the second common type of mechanical wave is one called longitudinal. So it's the exact opposite of transverse. So you're going to see Mr. Nichols push the material, the slinky, to the left, and the wave is going to travel to the left. So you'll see the little tape mark bounce back and forth. So the idea with the longitudinal wave is the medium moves along with the direction of the energy transfer instead of up and down or perpendicular to it. Okay? So having said that, let's go dig a little bit further into the vocab that really is the anatomy of the waves themselves. First of all, the wave has a little vocabulary all of its own that's not written down. The top right here, where you see the medium reaching its high point, that's called a wave crest. So that's the name that we give to one of the high points in the wave disturbance. And if the medium bottoms out right there, that one's called a trough. And what you've got then is a transverse wave, because the medium is bouncing up and down this way as the wave energy travels that way. Okay, so transverse again means at right angles. So what you're going to notice is they've got a little symbol. This is the Greek letter lambda, which we call the wavelength of the wave. And it's the distance between two crests, you'll notice. It's also the distance between two troughs or two any symmetric pieces on the wave. So you could nail down this little piece right here where the wave displacement's at 0 and headed down. And if I cruise along here, this is not a symmetric piece. This is 0 and headed up. I would head all the way to here. And again, you'd notice that that distance right there from side to side between any two symmetric points is called the wavelength. Now the last vocab word is really straightforward. It's right here, the amplitude. The amplitude is just the height of a crest or the depth of a trough, and that's really the thing that has to do with the energy of the wave. So one of the really interesting and amazing things about waves is that the energy really isn't in their speed. It's really in the height of the wave. So think tidal wave, and now you get the picture, okay? Okay, so let's just check out one more piece on transverse waves. So if you check out my graph here and you look at it carefully, you're going to notice that there's a change of axis, that this isn't distance anymore, that my transverse wave doesn't just repeat itself in space, so it looks the same, and also repeats itself in time. And so a thing that comes around again and again and again is called periodic. So we have what's called periodic motion when we look at waves. So in this example, you see what I've done is replaced the idea of wavelength with a term called the period. That's the length of time it takes for the wave to repeat itself. So get a feel for it maybe like this. If this is 1 second to get there, and 2 seconds of time there, and 3 seconds there, and 4, and so on, and out here is 5 seconds, then you should look, well, I have a crest here at t equals 5, and a crest here at t equals 1, so the period for this wave would be 4 seconds, the time it takes to repeat itself one time. Now, there's a flip side of period called frequency, and it's literally the flip side. So frequency goes by letter F, and period goes by letter T, and they are reciprocals of each other. So if I have the period, I could just take it and put it into this little formula. It's not even really a formula, but I'll do it. 1 over 4 seconds, and I just do the math, and I get 0.25. And rather than go around calling it 1 over seconds, people came up with a unit that's, as usual, a famous dead guy who deserves credit. This is called a hertz, big H, little z, and it's named after Heinrich Hertz, one of the granddaddies of radio. Okay, so before we go and wrap this up, let's go take a look at what some of this stuff looks like when we look at a longitudinal wave. So when you saw Mr. Nichols push on the slinky to create a longitudinal wave, what he was doing was creating a compression. Now you'll see this in class. The compression is really cool. It's a place where the slinky is squished together and it actually travels. It travels just like a wave crest does, and it travels down the length of the slinky. So everything being equal, if the idea of a compression is like a wave crest, then there must be something that's comparable to a wave trough. And there is. It's called a wave rarefaction. And the reason is when you push on the slinky to make an actual wave, you have to also pull back. So the idea of a rarefaction is that the slinky becomes rarer, so more spread out, and that also, that spread out section also travels down the slinky just like the compression does. So finally, the vocab for longitudinal waves works out to be exactly the same. They still have frequency, they still have period, and the distance between this compression and this compression is still going to be called the wavelength, as you can see them doing in their little diagram here. And there you go. So what we're going to do is to wrap it up with one last mathy example, and then we'll wrap it up finally with something cool that only waves can do.
You're going to time 10 seconds, and I'm going to count how many waves I make.
Okay.
Tell me when to go.
3, 2, 1, go. Stop.
22 waves.
So I wanted to pick that clip because let me set up this little math example, but it's a really good lab technique. Waves travel way too quick in the lab for you to time on a stopwatch how long it's going to take for the lab pulse to get from you to your buddy. It's just going to be too quick. So you saw what the teachers did. They figured out by counting for a long time how many waves they could make, and it's going to make the results come out much more accurately. So let's say you got 22 waves in 10 seconds and you have to figure out the period or the frequency. Here's what you do. Period is the time to make one wave. The big deal is when you have one of these fractions, you put the time on the top. So 10 seconds over 22 waves, and you just go ahead and make a fraction out of it, and you get 0.45 seconds. And that's implicitly 0.45 seconds for one wave, which is what the period is, right? So frequency, there's two ways to do it. You can just flip this number upside down and you get the right answer, or you can, which I think is a little more educational, you can just take this fraction and flip it upside down. So if I did 22 waves over 10 seconds, just notice that I put the seconds in the denominator, then what I'm going to get is 2.2 waves per second. And you remember what things or cycles per second is called? That's hertz. So again, it's big H little z is how we measure frequency. Okay. So finally, lastly, crazy cool thing that only waves can do. Let's go check it out and we'll be done. So interference is a thing that is unique to waves. If you throw two baseballs together, they bounce off. You throw two cars together, you've got a car crash. Waves do it differently. So what I've got is a little simulation I'm going to run by you. I'm going to show you a thing called constructive interference, where I've got kind of a square top wave pulse. This guy in the top image is going to run to the right. I've got a little bit of a round top pulse that's going to run to the left, and then in the bottom frame, you're going to see them collide. You're going to see one go this way and one go that way. And the big thing you want to look for is what happens when they're interacting and what happens when they're done. Do they bounce off, or do they go their own ways, or what happens? Okay, so let's check it out. So did you see it? What I hope you saw is the two things go through each other like nothing happened. Incredible. They add up while they're in contact, but then when they're done and nothing happens. So what you're going to see is a final example. Check it out and see if this works for you. Square top pulse going this way, we flipped the trough over, or we flipped the pulse here over and made it into a trough, and you're going to see the two of them again interact like this, and see if you don't get some destructive interference where the two of them cancel out. So we're going to go over that last example in class just to make sure everybody's got the real feel for it. But anyway, the definitions are yours, and that's it for now. Take care and have a great day. We'll see you real soon. Bye-bye.